All right, so welcome again, everyone. This is just going to be a very high-level overview of ROS. So let's begin. So what is ROS? ROS stands for Robot Operating System. It is not an operating system in the traditional sense, meaning it is not, the thing that all your programs and your computer runs in, but it's more or less a system of tools that help for you to build robots. So it's not an operating system. What it is it's a build and installation system. It's a development environment manager. It's a single or multi-machine launch system, a single or multi-machine process manager, a communication network, a parameter service, a community of open source packages, and a whole lot more. There's some links throughout this entire slide deck that'll be worth checking out. On to the next slide. So for today's plan, we're going to be focusing on the development environment managers, single machine process manager, some of the fundamentals of ROS and the communication, being able to launch on a single machine. For simplicity, we're going to be focusing on using Python today. If you don't know Python, don't worry, it's very simple. And then there's a lot of really great tutorials. Another thing, just to be clear about, so we're going to be focusing on ROS 1, specifically melodic. There's also ROS 2, which is completely different than ROS 1. A lot of the fundamentals are the same, but it does things a lot differently. So for today, we're going to be focusing on ROS 1 because that's what people still primarily use. And there's a lot of really great tutorials written for ROS 1. So we're going to be first talking about the developer environment. So in ROS, your developer environment is called your Catkin workspace, meaning you have basically a folder that is your workspace, and you have a series of packages. So packages just refer to a set of libraries or applications that define a specific purpose, right? So for example, I might have a vision package, right, that does all of my vision processing stuff. I might have an object detection package. I might have a motion planning package, right? So each of these packages are very specific. They have like a different set of libraries and applications associated with them. Inside of your source directory are what's called your Catkin package, like I just explained. So in order for a package to be considered a Catkin package, you have to have several things. One is, so this is considered means like by the ROS system. So the ROS system, the tools, look for these specific requirements to consider something a Catkin package. So it must have a package.xml file, which simply just defines the information about the package, the meta information. A CMake list. So a CMake list is just a way to tell CMake, which is a build system. It's basically a recipe that tells you how to build your libraries and your applications. And then each package must have its own folder. If you have nested packages or multiple packages, then you have what's called a Catkin meta package. And things are a little different with meta packages than with just regular old packages. I'm actually gonna go back and share my desktop because I actually want to show you some examples of this. So if you look here, this is my workspace, right? I have a folder and I have a source directory. All this other stuff is not necessarily needed for a workspace. And then inside of my workspace, I have several packages. So I have Magellan Core, Magellan Firmware, Gameplay, Motion, etc. Inside of like say Motion, I have my package.xml. So what does that look like? So package.xml just says like what's the version, Right here, what's the name of the package, a short description, who's the maintainer, license. It also tells you what your dependencies are. So I depend on ROS CPP, which is just the ROS CPP, ROS C++ libraries. It uses Catkin for building. It uses these different messages and message generation. So this just tells ROS like, hey, this is what my package depends on and uses, and ROS automatically figures out where to look for these dependencies. And then my CMake list just basically just sets some compiler flags. Tells it, so like just a quick reminder, this is like the recipe of how to build my package. So I tell CMake, okay, use this version. Here's some compiler flags. I need you to find these packages. I need you to generate, I need to add some messages, which will explain what those are a little bit later. I tell Catkin that this is a package and that there is an include directory. It also, and then I tell CMake to include my include directory, as well as to add any additional Catkin include directories. So Catkin automatically gets all of these, looks in all these dependency folders, finds their include directory, and then adds that here. And that's all under one variable called Catkin include directories. I tell it to add an executable. So this is the name of my executable, and then these are all the CPP files associated with it. This is like if you ever do like make homework1.cp.c-o homework1, right? So that's basically what you're doing here. You have your C or your CPP files. You have the name of your executable. Same thing here. So you can have multiple executables. Actually, you have 3 of them here. Then you tell it to link the libraries. So you build the executable, then you have to bring in your libraries. You add in your dependencies, and then bada bing, bada boo. You link those and your other targets, target aka your other executables, and then now you have your applications. So in ROS, your executables, your applications are called nodes. So that's what I'm going to call them from now on. So when I say node, that just means it's an executable. So there's a path follower node, a path planning node. So after all of this, you have several nodes. So what's really nice is that ROS abstracts out a lot of the redundant and painful things that you would have to do if you were to say like add all your dependencies manually. So by just defining everything in my CMake list with the specific ROS macros, ROS automatically tells CMake, hey, these are where all of my dependencies are, and everything just automatically just works. So ROS, this is again, as ROS as a build tool, as a developer environment, it makes it really easy to define your recipes for building your nodes. So now I am inside my package here. So let's go back. Okay. So I would like for you guys to follow along. So there is there's a tutorial here. So in this tutorial, it's about how to create a Catkin package. And I'm also going to follow along here as well. And we're going to make a package specifically called RAS Workshop. So we're going to have this here. So what makes up a package is exactly everything I just said. So we're going to make a workspace here. So first thing you need to do is make a workspace. So I'm just going to call it RAS Workspace. Then the next thing I want to do is I need to call this Catkin create package. I also need to make a source directory. And then go into source and do Catkin create package. And then I'm going to call it RAS Workshop, I think is what I said to call it. Yeah, RAS Workshop. And then these other arguments here are your dependencies. So we're just going to do standard messages, which I'll explain what those are in a minute. And then ROS-Py, so that's the ROS Python libraries. So when you add those, if I were to say now go into RAS Workshop and look at the package.xml, it automatically tells it that it depends on ROS-Py and standard messages. If you don't have ROS installed and you can't follow along, that's okay. But if you do, it'd be great if you could follow along. Okay. So let's go back to the slides. Okay. So now we have our package. Now we got to create some nodes. And before that, we need to talk about how does ROS help you with your nodes. So your processes, like I said, are called nodes. A node is a single running process that does one particular thing. So the benefit of ROS versus other tools is that you can have multiple running things that do one particular thing. For example, I could have a cone detector node or a Roomba detector node or a vehicle detector node. So instead of excuse me, instead of like an Arduino where you have everything being one giant executable that you flash on your robot, or like say like you're writing something for your 1501 class or your Intro to Java class, you have everything in one giant main. That makes it very difficult to develop, especially when you have very complicated processes, very complicated behaviors that you're trying to create. And it also makes it very difficult to modify things later. So the benefit of ROS is that I can have multiple nodes that each node does a very specific thing. So you want each node to have a very defined function, and you want it to have very specific things it's doing, and it should not have a lot of codependence on each other. Meaning it should only depend on its inputs and then do some outputs, right? There are exceptions to this, but you want to be careful about the way you're designing your system, right? You need to know is what I'm designing, should it be a library or should it be a node? Should it be like multiple nodes split up? So that's more of like a software engineering thing. What ROS provides is just the tools that allow you to do whatever you want. And so ROS takes care of launching all of these nodes for you, and we'll explain that a little bit later. So again, going back to the ROS tutorials, there's another tutorial that explains nodes in detail. So give me 1 second. Okay. So we're gonna be making our first node. There's also some example code that you can follow. Here it's like pretty simple. I'll post it in the chat anyway. Okay, so first thing we need to do is create a new folder called RAS Workshop inside of source. So what I'm doing here, why I'm calling it RAS Workshop, is because typically the recommended way to have Python libraries with ROS is you have your package name is RAS Workshop, and then inside of that you have inside of your source you have another folder directory called RAS Workshop as well, which is the same as your package name. So your Python package, it's typically good practice to follow your package name. If you have multiple Python packages, then you want to name those appropriately. But usually you're going to have one Python package per ROS package, per Catkin package, but there are also exceptions to this as well. This is just a good practice to at least make sure you're following like the Python naming conventions with ROS. So another thing we want to do is create this init.py. This is just boilerplate that is required to make sure that they know that it's a Python package. And then you create a file called myFirstNode. This is definitely not my first node, but we call it that anyways. So now let's look at some of the example code, and let's explain what's going on here. So this fancy line at the top just tells your shell. So I'm inside of a shell, right? And I use fish here, right? So this is a fish shell right here. You could also, use bash, right? So again, this is bash. So I personally use fish. So this just tells your shell that when it goes to execute this file to use Python, if say I'm using Python 3, I would say Python 3, but for this we're using Python 2, so you just say Python. We need to import the ROS libraries, so those are called ROSPy. And then in Python, the way you define if you have a main is there's this environment variable called name, and you check to see if it is equal to main. This is so you know if in Python's file can be imported or it can be directly run. If name is equal to main, that means it's been directly run and not imported. So if I were to import this file, whatever I have after this point doesn't get executed. Or if I running this file from the command from the shell, then what will happen is then this will actually be true and then it'll execute. So again, this is just if you're not familiar with Python. So the first thing we always do in every Python, or rather in every ROS node, is we have to tell ROS that this node exists. So we do rospy.init node, and we say what the name of our node is. So you can call your node whatever you want. I just called it test node. Then there's there's this function here called isShutdown. So rospy lets you know whether or not the whole system is being shut down. Basically, every time you launch your ROS nodes, there's what's called a ROS master. Your ROS master is what handles execution of all the nodes. It handles coordination between all the nodes. And if there's a shutdown request, that goes to ROS master, and ROS master takes care of telling all the nodes, hey guys, we're shutting down. You need to shut down your node. And then if the nodes don't respond, then it kills the nodes. But they should respond and exit cleanly. So I check to see if we're in shutdown, and while we're not in shutdown, then we're going to print something. So log warn throttle just saying print something once every second, and whatever we're going to say, my first node. So every second we're going to print this. Cool. So there's several ways to run stuff with ROS. So I'm going to just show you one of them. You can run stuff directly. So this chmod plus X is just telling it to make it an executable. It's green, so that means it's an executable now. So over on this side, I'm going to run ROS core. That just launches ROS master, right? So ROS master is running on this port on my local host. And it has this PID. This is the process ID. Shows you what the parameters are and whatnot. So then I can come in here and say like my first node, and now every second it'll print. So this is a timestamp here. This is so you can see like 1 second later, prints. So it'll just keep doing that for infinity until I kill it. I can also come here and, well, that doesn't die. So, all right. So that's our first node. So next we're going to be talking about communication. So one of the nice things is, so I said, oh, you could have very specific nodes that do a very defined task, right? And you may be wondering, well, what if I need to send information from one node to another, right? Well, ROS has built in this communication network that allows me to send messages from one node to another. So here is, so there's this package called standard messages, and one of them is just called a string, right? So I define a string, which is a primitive type. The field is called data. So the data is of type string, and that is my message. There's other messages as well. There's a bool, which is like a boolean. There's a byte. You could also have arrays. So you have an array of primitives. And then you can also have what's called nested messages. So I have my primitive here, and then I can take my primitive and define a new message, right? So I have a new message. That's unt, data offset. And then once I have my message, I can use that message in new messages. So at the lowest level, this multi-array dimension message has a label, a size, and a stride, right? Which are a string and two 32-bit unsigned integers. Then that message is called the dim in this message type. And then this message type is used in this message here. And so now you have one message that has all these different nested types. And you can actually see this. If I come here, there's a, what's it called? A command line tool that shows you what are all the fields in a message. So we have a float 32 multi-array. And you see here, so you have a layout, which is of this type right here. And then a layout has a dim, or this multi-array dimension, which has this layout here. So these are all your fields. So you would do message.layout.dim.label if you wanted to get the label, or message.layout.dim.stride in order to get the stride, or message.data to get the data, et cetera, et cetera, et cetera. So these are all your fields that are all part of this message here. So you define these messages, these message files that just basically say exactly like you do here. You have your type, the name of the field, and you lay out a whole message that way. So then ROS then can take these message files and compile them for multiple languages. So for Python, for C++, for JavaScript, for multiple different languages. And this allows communication between multiple different languages as well, which we'll get into a little bit more. So once we have these messages, we need a way to send these messages to each other. So we have what's called a topic. I think this is a slightly better visualization here. So basically, what happens is that you have a topic, right? And it has some defined name. So he just gave it some number. And you have what are called publishers and subscribers. So your publishers publish the data to this topic. Your subscribers subscribe to this data from this topic. So this topic, you provided a name. So there might be a global map, for example, if you're sending out a global map. It might be a vehicle detection if you're detecting vehicles. It might be an odometry, which just tells you where you are and how fast you're moving. So you could call this topic whatever you want. You could namespace topics, meaning say you have multiple robots all connected to the same ROS master. You could have multiple different names for each specific robot. And so what happens is that on startup, ROS, so these nodes tell ROS, hey, ROS, I'm going to be publishing data of this type. So let's say it's a string, standard message string, and I'm going to be publishing it on this topic here. And then ROS says, okay, I've registered that you are publishing on this topic. Another publisher comes along, it might have a different topic, it might be the same topic. If it's the same topic, you have to make sure that they're the same type between the two nodes. Otherwise, ROS will crash. It won't know what to do. It'll throw errors. So you have another node tells ROS, hey ROS, I am a publisher and I'm publishing on this topic with this type. ROS keeps a dictionary of all the nodes that are publishing to that topic. And then when your subscriber comes along and says, hey, ROS, I want to subscribe to that topic, right? Can you whenever you get a new message, can you forward it to me, right? So what ROS does, it tells that node internally, hey, you need to talk to this publisher and this publisher here. Whenever these two guys publish data, they will automatically connect to you and you will get the data. So ROS here is just sort of, plugging the wires, right? It's acting as if like back in the day you had phone operators, right? It's telling the different nodes, hey, you guys are all exchanging on this topic here. Here's where this topic exists. Here's the endpoint for this topic. You guys can all subscribe to that topic and you guys are all publishing to that topic, right? So then when these messages get published, aka get sent onto that topic, those messages automatically get shuffled to all of the subscribers that are subscribing on that topic. So this allows inter-process, aka between process, communication between all of your nodes. Okay. So, yeah, again, this works across all nodes, no matter what language was used to write it, as long as ROS has libraries for that language, which, for example, for like ROS2, there is a multiple of languages that have ROS support now. So it works across nodes. It's agnostic. So the publisher is agnostic to what the subscriber is. The publisher doesn't even know the subscriber exists. So it can work independently of them. So we're gonna go through some examples here. So this is the publisher node. I'm gonna post this in the chat. Here's the subscriber node. And then we're gonna follow along. So I'm just downloading the nodes because I don't feel like typing them out. Okay. So let's look at these side by side. So we have the publisher node, and then we have the subscriber node. So again, like before, okay, we tell it we're in Python, we import ROSPy. Something that's a little different now is we have to import the message type. So from standard messages, we're importing string. You could also import other ones as well. So it could be float or whatever, float 32, so on and so forth, right? So things are a little different now in the subscriber node. So we define this callback function. You don't have to call it callback. You can call it whatever you want. You just have to create a function that takes in a single argument, which is message, your message here. And I have my subscriber here. So, okay, I have my main, I create my node, which is subnode. I create this subscriber here, this object. I tell it, here's the name of my topic. It has type string, and I want you to use this callback here. So in ROS, there's this concept of a callback where every time I get a new message, this gets called, okay? Which is not exactly 100% true because there's like different threading models, but for all intents and purposes, you can think about it as every time I get a new message, this gets called. This rospy.spin just tells ROS, okay, while we're not shut down, I want you to just spin, just do nothing. Only thing I want you to do is keep servicing my callbacks until ROS is shut down. So that's the subscriber node. On the publisher side, we create a rate. This just says like, okay, in this loop, I'm going to execute this loop at 5 hertz. So that's what this is right here, saying 5 hertz, so 5 times per second. I'm going to create a publisher, also on the same topic. It has type string. The other thing to be aware of is there's this queue size here equals 10. So what this is saying is if I cannot connect to this node here, so if subnode loses connection to my publisher node, I'm going to keep a queue of the 10 most recent messages. So that way, if messages, so this prevents messages from getting dropped. You can create this queue size however large you want, but if you're on a very poor network, you don't want to have a very large queue size. Otherwise, then you'll use a lot of memory. So that's all what queue size here is defining. I usually just use 10 because why not? Seems to be what everyone's doing. So I create my message, just another object. I say message.data equals I can publish, which is just a string. I publish that message, and then I sleep for, 200 milliseconds, because it's at 5 hertz. So here's my 2 nodes. Let me see, so unlike last time, I'm just going to leave these as is. But I also, again, we need to make them executables. So now they're executables, that's why they're green. Okay. So next thing we're going to talk about is launching. So last time you saw I had to start ROS core and launch the node directly from the shell. After a while, this gets really annoying if I were to have to launch each thing individually myself. So ROS makes it really easy to define what they call launch files that can start all your nodes, load your parameters, map topics, and do so much more. You can literally run Python inside of a launch file, limited Python functions, so you can have some very complex behavior based off of your environment variables, your arguments, your parameters, etc., and so on and so forth. So we're going to have another example file here already defined for us. So here it is. I'm just going to download it so we can look at it together. So where do I put launch files? You do not put them in source. So I go back to my package, and what I do is I make a directory and I call it launch. And then inside of launch is where I put my launch file. Okay, so again, just to reiterate that, so I'm in my package, my Catkin package root. So if I were to go up, right, if I go to RAS, workshop, source, right, so workspace, I'm still inside my workspace, source, inside my package, launch. So here's my launch file. And then I go here, and I say node equals pub node, node equals that. Now, before I can actually run this, I need to do some work. So I need to go to my workspace directory root, and I need to run a command called cac build. So you might be thinking, well, Andrew, these are just Python files, right? Why do I need to run cac build? Well, because cac build also does a lot of like copying and generates some files that tell the ROS environment, hey, there's this package that exists inside of here, and it has this launch file here. So when I go to launch it, it can find that launch file and launch everything properly. It can find all of these nodes properly as well. So I need to do cac build. So it does its pre-tool stuff. And then it found this package and it built it. Obviously it didn't take long because it was all in Python. There's this node at the bottom. It says workspace packages have changed. Please resource setup files to use them. So what does that mean, right? So I have another pretty nice visual here that I want to show you. So pre-build, I have my workspace, I have my source, and then I have all my packages, right? After I build, you have now 3 new folders, right? There could also be a 4th, depending on if you're using install or not. So you have Devil, Build, and Logs. So Devil is your development folder. This is where all of the all your binaries, your executables get copied to, get generated to, and whatnot. Logs is logs, and build is your build output and whatnot. So if I look here, I have my build, my devil, my logs, and my source. These 3 were generated. So if I go inside devil, I have a bunch of files here. I have this setup.bash. I have a setup.zh and whatnot. If I were to go to share, I could see, oh, there's, you know, some CMake stuff that was generated. If I go to lib, you know, more stuff generated. So these are all just generated files and whatnot. So I can ignore them. So my shell automatically configures this as a workspace. But what this means is that I'm sourcing this devil.setup.bash. If you're in bash, you just run source and then devil/setup.bash. Because I'm using fish, I need to do bash source that because I'm in fish. I can just quick demonstrate this in bash though for you. So you just do source devil setup.bash. Again, yep, this is bash, this is fish. Now if I want a ROS launch, all I need to do is type ROS launch, the name of my package, so it's RAS workshop, and then automatically ROS, just by clicking tab, automatically ROS finds that I have this launch file inside of this package. So once I hit enter, why is it doing that?
Did you source setup.bash in the folder that you're in the terminal that you're running the code?
Yes, yes I am.
Cool.
Yes, I am. Oh, so here's my mistake, right? So if you looky here, so I named my package RAS workshop, but here in my launch file, I did RAS workshop example. So let's go over this launch file format. So I have these node tags, it's just XML. And I say, what's the name of my node? It's called pub node. It's inside of this package, right? This package doesn't exist because I named it RAS workshop and not ROS workshop example. So then I just need to rename that to RAS workshop. So the nice thing about launch files is that they're not, you can launch a node from any package. So I can have this can be as long as I want, and I could launch nodes from any package. So this is just telling ROS, look in this package and launch this executable, right? So this type just says what's the name of the executable. If it's C++, remember that the CMake list, I define the name of the executable. I would put that there as well. But since we're in Python, I just provide those. And then let me save that. And then in theory, this should just work out. There we go. So remember, I say, I can publish, right? So if I go to source, let's see, let's look at the subnode, pub node, right? So so my message is I can publish, right? And that's right here is where I'm publishing. So if you don't believe me that this is getting called, I can also do rospy.logwarn. Yep, you saw how automatically when I hit Control C, everything, it killed this node, it killed ROS out. ROS out just manages your standard out, like the printing and stuff. And then master just going down ROS master. So then I relaunch it, and I say, okay, look, I'm in the callback, and I can publish. So this is spamming really fast. So in callback, I can publish. Okay, so there you go. These two nodes are now communicating with each other. And we can launch it from one place. So let me go back to this. Okay, so this is the extent of what I was plan on covering today. Again, I'm going to share these slides so you guys can look them over, but just some further resources. So today we only covered ROS-Pi. We didn't cover ROS CPP at all. The high-level concepts are the same. It's just different syntax for different things. And there's also some additional complexities because you actually have to build your C++ nodes. The ROS tutorials and wikis are bless me. Oh, excuse me. Lay out a lot of this information. They lay it out really well. And they provide a lot of useful information. Let me just show you real fast. So there's some of the core ROS tutorials about some of the basics we covered, how to install, how to navigate the file system, the ROS, how to create a package, how to build a package, what are nodes, what are topics. It also starts covering more complex things like ROS services and RQT, how to use ROS edit, how to create a ROS message, simple publisher and subscriber in the different languages, and then a simple service and client, bags, which are, so you can create a bag file, which is I just can save every message that gets published to a topic, and that all gets saved to a file. So that's for like if I want to debug my code later, that's what it's useful for. And then additional things like creating ROS packages, running ROS across multiple machines, custom messages, and more advanced things as well. The ROS tutorials are amazing. They're very well laid out. They're probably the best set of tutorials that for any large open source package I've ever seen. So highly recommend looking through them. Yep, and then feel free to always ask questions on Slack.